This video contains a very brief introduction to geometry optimization techniques. Typical tasks for geometry optimization would be either to locate a minimum structure. It could be, for example, the structure here. It could be to find the global minimum structure. That would be this one here in the drawing. Or it could be to locate even a transition state structure, either this one here or that structure that we have over here. The 3 points that we discussed on the slide before, that is the maximum, the local minimum, and also the global minimum, these points are characterized by having a gradient equal to 0. We remember here that the gradient is defined as the partial derivative of the energy with respect to a given geometrical parameter. Such points here where the gradient is equal to 0 are called stationary points, and these include both the minimum, the maximum, and also the saddle points. So it becomes very important for us to be able to search on the potential energy surface and to locate those points where the gradient is equal to 0. In order to characterize the different points on the potential energy surface where the gradient is 0, we need information from the Hessian. And again, we remember that the Hessian is defined as the second derivative of the energy with respect to two geometrical coordinates. So at the minimum on the potential energy surface, all eigenvalues of the Hessian are positive. At the maximum, all the eigenvalues of the Hessian are negative, and a saddle point is characterized by having some eigenvalues negative and others are positive. In particular, a saddle point which has only one negative eigenvalue is called a transition state, and this was what was illustrated on the slide before. So let's see here how we actually do in order to locate a local minimum. For this, we can use different kind of methods, and we can group the methods into so-called first order methods, which makes use of the energy and the gradient, and second order methods, which make use of the energy, gradient, and also Hessian. It is also very important to remember here that in numerical calculations, due to the finite precision, we never have a complete zero gradient, but we only have a gradient which can be smaller than a given predefined cutoff value. And when we calculate a gradient to be smaller than this predefined cutoff value, let's say 10 to minus 4, then we define this gradient to being equal to 0. But this is due to the finite precision in our calculations. So if we look here at a first order method, then one of the most used methods is called the steepest descent method. What we do here is that we start out on a given point on the potential energy surface, and then we take a step in the negative direction of the gradient. We illustrate this here by saying that the step is equal to minus the gradient. Usually we multiply the gradient by some scalar in order to adjust the step, being either a large step or being a small step. But the important point is that we simply follow the negative of the gradient. And this of course makes sense, since the gradient tells us about how the energy changes when we change a given geometrical coordinate. Moving in the negative of the gradient then means that we will be taking down in energy, that is towards the minimum. At some point we will meet the situation where the gradient becomes 0, and then the step will also become 0, and we have located the energy minimum. Another first order method that is used a lot is the so-called conjugate gradient method. This is also a first order method like the steepest descent method here, but here we do not take a step directly in the direction of the negative of the gradient of the current point, but we add some of the step related to the previous point on the potential energy surface. That is, the optimal step here is a linear combination of the gradient in the given step plus information about the previous steps we have taken in order to reach position number I on the potential energy surface. Mathematically, this turns out to have a much better convergence than the steepest descent method, meaning that we need to take fewer steps in order to reach the energy minimum. Thereby, we can actually arrive at the energy minimum faster than we can by using the steepest descent method. A minus with this method, of course, is that we need to store the history on our movements on the potential energy surface, but really this is only a vector that needs to be stored, so this is not very memory consuming. An example of a second order method is the Newton-Raphson method, and what we do in the Newton-Raphson method is that at a given point on the potential energy surface we make such a second order Taylor expansion of the potential energy surface. That is, we approximate in a local region the potential energy surface to be equal to a second order expansion. Then what we do is that we find the minimum of this second order expansion here, and it turns out then that it gives us then the information on the step that we should choose in order to go to the minimum, the step D here, which we can calculate as minus the gradient divided by the Hessian. That is, if we have a one-dimensional motion. If we don't have a one-dimensional motion, then it's the gradient here multiplied by the inverse of the Hessian matrix, and then of course we have the minus in front here. So if we are in a position now where all the eigenvalues of the Hessian are positive, that is, we are rather close to an energy minimum on the potential energy surface, then we will actually take a step again in the negative of the gradient. On the other hand, if we are in a region where we have, for example, one eigenvalue which is negative, the other ones being positive, meaning that we are rather close to a saddle point, then we will actually take a step in the negative of the gradient in all directions except one, namely the one that defines the saddle point, where we will actually take a step in the positive of the direction. This means that we will move up in energy actually. So by using the Newton-Raphson method here, we are able both to go up and to go down in energy. It converges very efficiently, especially when we are close to stationary points. And as said before, a characteristic of the Newton-Raphson method is that it converges to the nearest stationary point, regardless of this being either a minimum, a maximum, or a saddle point. The Newton-Raphson method involves the calculation and the use of the Hessian. This matrix here, the Hessian, can become quite large if we have a large molecule, and it means that the Newton-Raphson method is not practical for optimizing large-size systems, simply because it can be very difficult to handling such very large Hessians. So some good practices for geometry optimization here would be to start by relaxing your structure, especially if this is a poor starting geometry obtained from some experimental source, for example, using a steepest descent method and then a loose zero gradient criteria. Having now a structure which represents the molecule better, you can refine the structure using, for example, a conjugate gradient method and then a more tight zero gradient criteria. Should you experience problems using this conjugate gradient method, then you can try to switch to the Newton-Raphson minimizer. But remember here that the Newton-Raphson minimizer involves the use of the Hessian, so it can be quite time-consuming to use this method here. Remember that you should never use the Newton-Raphson method as a start-out method if you have a bad starting structure. And this is simply because for such a bad starting structure, you are far away from the true minimum energy structure, meaning that your Hessian at the point where you start out will probably contain maybe a lot of negative eigenvalues, meaning that the Newton-Raphson method will not take you to the energy minimum, but it will instead take you to some saddle point on the energy surface. So for the bad starting structure, always start by relaxing it using a method with a guarantee of going down in energy, for example the steepest descent method, and then you can refine your structure using either conjugate gradient or even the Newton-Raphson minimizer. When we do the geometry optimizations, and especially we're here when we do the first order geometry optimizations, then these methods will always take us to the nearest minimum. So if we start out on this simple potential energy surface at this point here, then when we do the energy minimization, the method will take us to this point here. But if we start out here, then the method will take us to this point here. And this here is of course the true global energy minimum, but we will never be able to reach this point here by such first order methods if we start out with a structure that represents the point on the potential energy surface here. So we have to be very careful when we rely on geometry optimization, and a method that can be used in order to, well, maybe not secure, but at least to make us more certain that we have actually reached the global minimum energy structure, is to combine minimization techniques with so-called conformational searches. And we will do those conformational searches during the exercises in this course here. Basically, what we will do in a conformational search procedure is that we will use the program to define a lot of different starting conformations for our molecule, and then using these maybe 100 different conformational starting structures, we will be doing an energy minimization, and in the end we will then choose the structure that has the lowest energy as the one representing the global minimum energy structure. Exactly how to set up such conformational searches here, we will go through this when we do the exercises relating to geometry optimizations later on in this course.